Hello friends, welcome back to the bench. Our patient is here. This is a AsRock Z790 Micro. It's really nice, really tiny, cute little board. Like it's about 7 inches by 7 inches. Like I got a picture of it before it was delivered. And I did not expect it to be this tiny. It did seem kind of small on the picture, but yeah, the socket seemed unusually large for the board when you see it on the picture. Anyways, it's here for a 1700 LGA 1700 socket replacement. So that's gonna be my first. But you know, how different can it be from 1200? It's a little wider. Actually, I'm not even sure how much wider. It looks like maybe it's a little more narrow in this direction and a little wider in this direction. Anyways, as you can see, it's prepped, not by me. That's how it came in. All right, so there's plenty of aluminum foil everywhere. So I haven't really seen the board yet. I see that there's a PCI Express port over here. There's 2 memory banks over here. I see 2 clips. Yeah, so we can put 2 DDR4, I believe, memories in it. And there's some I/O, but we can't see it yet. So I was going to unwrap it completely to analyze it because there was a prior repair attempt or replacement attempt. But looking at it like this, I checked from various angles. I don't see any signs of overheating. Brian said that he heated up the board to 380 degrees for 15 minutes. Well, judging by what I see over here, the board never reached that temperature. I assume that was hot air. But here's the trick. So typically, when you use hot air, the thermocouple in the hot air station is located on the heating element. So that 380 that you set up is the 380 on the heating element. Then the air flows through the heating element and flies out the nozzle and heats whatever it needs to heat on outside. But the air is a very poor conductor of heat. So even considering that we have 380 over here, we're gonna have maybe 360 over here, 340 over here, and maybe 320 over here, right? So with hot air, you work a little bit different than how you do with the IR. So perhaps the hot air station was set to 380, but the airflow was really slow, perhaps. The hot air station maybe is not well calibrated, so the actual temperature maybe was 340, which at the end of the nozzle and blowing at the board was maybe 280. Right? If it was 280, this looks good. 280, it's a little bit above the socket maximum temperature, because typically maximum temperature you should use on the socket is 260, the real actual temperature on the socket. Above that, it will start deforming, melting. You're gonna see some signs of melting especially on the surfaces. But if we look at the socket from up close, there is no sign of melting. There's some flux left over. So even judging by how the flux was flowing, I wouldn't say this was heated up properly. Right? We have some physical damage here, right? Because probably you were poking at the socket from this side. To see if it's loose, but not a sign of melting. No signs of melting on the board. If you take a look over here on the board around, there are no signs of bulging. It looked a little bit here and there, but it's probably just a flux. And inside, typically, the nozzle is going to be in the center, and the highest temperature is going to be in the center by these caps. So I've had plenty of boards that I damaged that had bulging, but only here in the center, right? And the rest of the socket, where the socket sits on that area, it was fine, but it was bulged up in the center. And when I tried testing it, it wouldn't work. So once there's bulging, there's probably not much you can do, because some of these traces are really tiny, those data traces, and they sit on top of the big planes of copper, and those big planes bulge up and basically essentially just breaking those tiny traces on the board or inside the board. It's unrecoverable. I mean, I could think of at least one technician on YouTube that is capable of fixing stuff like that, but that wouldn't be worth it. So this is fine. So my conclusion is that you were not treating this with temperature high as you thought you were. There is no way this was treated with 380. This socket would have been completely molten in 380. Now the second thing is the outline. Look at I already took the picture, but again, we have a socket that it aligns with the top line, but doesn't align, well, actually it kind of aligns, you see, it aligns with the right line, but not with the left line. It goes over the left line. See that? So that's going to be difficult to align. See, here it looks like it aligns. All right, but when you go up here, this looks like it goes a little bit over. So I don't know if the socket is deformed due to heating, maybe, or the outline is what it is. Because there's no way the socket is not sitting right. Although, yeah, there is a possibility that the solder loosened enough that the socket shifted slightly. I guess it's possible. I was thinking of throwing it into the ultrasonic cleaner to analyze it better, but I would have to remove all of that foil, all of that protection. Which I don't want to do if I don't have to. So I just decided I'm just going to take this socket off, clean the board, and see what we're working with. The only problem here is, where do I put my thermocouple in? And I think I'm going to place it here because I have the most room over here. I like to put it on this side, but we have a lot of aluminum foil over here that will interfere. Now I'm going to put a second thermocouple on this side. And that's going to be external thermocouple, not attached to the control circuit. It's only going to give us the temperature, the temperature reading. It's not going to affect anything. And I'll show you how I do it. Now I did receive replacement thermocouples, but I haven't figured out how to use it yet. So I'm going to use the regular thermocouple. Placed over here, stuck with a Captain tape, and that's what we're gonna do. Alrighty, let's get the machine out. You probably can't tell, or maybe you can, but I have a lot more room over here now. I trimmed this little shelf over here by 5 centimeters. That gives me a more room to put the machine over here. I can't extend this microscope any further, which it was more comfortable when the boards were here, where this was my center. I just kind of got used to that. Now it's a little further, so technically I have more support for my elbows, so maybe that's better for my hands, but now I just have to get used to it. It seemed a little easier when it was here. So, there's drawbacks to everything. But I could also extend this little pipe over here, and I have some concepts of how to do it. So that will be the project when there's nothing in the shop and I have time. All right, let's get the machine and let's start heating it up, remove the socket and see what's underneath. Okay, so we have a second thermocouple placed at the top of the socket and our main thermocouple, which is controlled thermocouple, at the bottom. So we'll see the temperature difference. Now, one thing that I improved, or I'm trying to improve now, based on that last board that has proven to be very difficult to remove and resolder the socket, especially without melting. The main issue that has been identified by Scratchy was that the bottom temperature was not high enough. So yes, that was definitely the issue with that board. This one is a lot smaller, but this is the socket we haven't worked on before. So what I'm going to do is increase from 130 to 155 for this board, because it's a small board. I'm thinking of going no lower than 160. Scratchy suggests not going lower than 175. Or was it 185, and all the way to like 200s. And that seems like a lot to me, because remember we were measuring the actual board temperature. The thermocouple at the bottom is sitting on the board, it's stuck at the board. So it's not the temperature of the heater, it's the temperature of the board. So that seems a little bit intrusive on the high end. Everything here is lead-free solder, so it's not like it's gonna start flowing, it's not like the components are gonna start just falling off the board. But if you heat it up to 200 degrees, you can, if you smash the board, you can dislodge some components. They can fall off because the solder is not flowing, it's not melting, but it's soft enough that it could happen. Well, obviously we're not going to be smashing the board when it's heated up that much, but still, my idea is to just do this procedure at the lowest temperature possible. Our last board, that was the lowest temperature possible, which has proven to be difficult. Very difficult. And so now I'm going to compensate with a little higher temperature at the bottom, and that should make the process a lot easier. And that, in which case, perhaps 235 will be enough on the top heater. We'll see. Let's start heating it up. So let's switch to program 0 preheating. Let's hit it, and note, as you will be watching the speed up footage, the vision from this camera, from this tiny camera here, you will see how the socket drops by a good 2-3 millimeters down as it heats up, and then goes back up when it cools down. That is the board flexing. It's not even the board flexing, it's the copper inside deforming. As I said, there's no way around that. You just need to accept that this is what's going to happen. And no matter how no matter how well you install the board, it will always be deforming, because that's the laws of physics. Alright, now the question is this socket lead free or tin? If it's lead free, it's gonna start floating, it'll drop at around 200 degrees, that we'll see over here. If it's tin, it should sit at 235 because there were no issues removing the socket at 235. Mainly because the board is small, it soaks a lot of heat, it doesn't radiate that heat quickly, so it remains hot. It was relatively easy. The single 235 program was enough. On the previous socket, which was AM5, so a little larger, I had to switch to program 5 and keep it on I think 245 even for a little while before the socket fully loosened. So this should be textbook. Let's see. Alright, that was complete textbook job. As you can see, it dropped at 235 very nicely, just few seconds on 235, and it nicely dropped. I don't know if you caught that. The board doesn't seem to deform as the other ones do, but that might be also because I use higher bed temperature now. Could be. We had some kind of residue on the Captain tape over here that was smoking. It was too late for me to remove it, so I just let it be. The socket seems to be aligned properly. As far as I can see, it looks pretty good. It dropped uniformly, pretty much the whole socket. No signs of overheating, no signs of melting, nothing like that. It looks like it's gonna be a successful replacement. Now let's let it cool down, run it through the ultrasonic cleaner, and go from there. Alrighty, it is done. Actually, the most challenging part of this was cleaning it. And why was it so challenging? Because my flux mixed with customer's flux, and it created this rusty looking, you can still see it, it's not perfectly clean, but it's a lot better than it was, that's for sure. I don't know, it just created this kind of mixture that I couldn't remove with an ultrasonic cleaner for some reason. I gave it I don't know, 30-35 minutes in the bath, and it wouldn't budge. So finally I tried using the brush, the paint brush, and it finally and working a little bit with tweezers, getting all those specks. It's not perfect, but I tested the continuity. Everything looks good. It would have been perfect if it wasn't for that cap. You can see that I replaced the cap over here. This one over here, and I gotta review the footage. I'm pretty sure if it was like that when I received it, I probably would have noticed it, but I noticed it after cleaning, after everything was ready, and it has proven to be extremely difficult to remove that cap. As you can see, it's right next to the socket, and I melted a little bit of the inside of the socket, but that's because mainly because I touched it with a soldering iron tip. Then I had to increase the temperature to actually desolder those caps, and that also caused slight melting over here. It's not a big deal. It shouldn't affect anything. The socket is perfectly fine. I might run it through one last cycle of ultrasonic cleaning, but the trick is, or maybe the concern here is that if you oh, here is the cap. Oh, you see, because I lost it and I couldn't find it, so I replaced it with this cap. But now I see it. I found it. Okay. Too late. I already replaced it. Anyways, now the concern with too much ultrasonic cleaning is that you might damage the board, you might damage the components, because there is such a thing as too much cleaning. So I didn't want to overdo it. It looks perfectly clean. Well, outside at least. Well, maybe not perfectly, but clean enough. It also cleaned all the rest of the board. Everything looks nice and clean here, right? Because there is some residue left. Oh, here's still some residue left from the thermal paste. There. It's a lot easier after ultrasonic cleaning. But the main purpose is to clean the flux off the socket. That was my main concern. As you can see, there's still some of that goo left inside the socket, but that's not a problem because we only care about the pins being clean. The rest, if there's some stuff left inside, as long as it doesn't conduct, it's fine, and this doesn't conduct, it should be okay. But we'll see. I might run it through one last cycle of cleaning, because I still see a lot of that stuff over here, right? Yeah. But here, that's not a problem. I'll just use toothbrush and alcohol, and it'll go away. The inside, I can't use the toothbrush because one wrong move and the socket is done. And I really don't want to replace it again. Although on this one, since the bed temperature was higher, I think it was a lot easier because of that, but also the board is tiny. It's very easy to work with. I wouldn't mind getting more of these. It's extremely easy to handle, right? It's very nice board. It's I like it. And and you can put 2 more SSDs in the back. I didn't even see that. 2 more SSDs, and 1 SSD goes here over the PCH. I don't know how that works. I guess they share the heatsink. Yeah, it's really nice. It's a really nice board. So the socket that we had was this. So I guess at least it is better, right? Maybe it's not perfect, but it's definitely better. And I'm curious, it should work. The other thing that I noticed is that this board doesn't seem to want to deform as much, and probably part of that is because I used higher bed temperature. Maybe. I'll keep testing that, but maybe it's the construction of the board, maybe because it's smaller, who knows. But it definitely did not experience, I didn't see any. I'll review the footage. I haven't reviewed the footage yet, but I haven't seen any deformation of the board during the process. Alignment, it wasn't too bad. It wasn't too bad because we have this corner. I specifically focused on this corner. Now every corner is nice and solid, right? There's no play, so we are soldered well. There was I clearly saw the moment it dropped. So and it dropped pretty much straight down. It didn't align itself, so it was already pretty well aligned when I started heating it. And it looks good. I think it's good. It's, if it wasn't for, so the thing that didn't go well was this unfortunate cap, and I'm pretty sure I moved it when I was removing the socket, or during the cleaning process. That's also possible that I moved it when I was cleaning it, but most likely I moved it when I lifted the socket. I might think of better ways to lift the socket to avoid that, but typically it doesn't happen. Usually I don't move those caps. In this case, well, sometimes something has to go wrong, or maybe in every job something has to go wrong. This looks like the I/O on this board is also pretty interesting. We have display and HDMI. We have two USB-Cs. We have an array of USB 3.0, I assume. We have built-in Wi-Fi, and we have optical output for the audio. Very nice. For the size of this board, we got only one 8-pin connector for V-Core, but LGA1700 that can pull serious CPUs over here. Only 2 DIMM sticks, but 8 gigs each, or you can even get 16 gigs each, and you got 32 gigs of RAM. You don't really need much more. And plenty of IOs, plenty of we can put 3 NVMEs here, which I didn't expect was possible, and everything locked in 7x7 inch box, or maybe 8x8 inch box. It's really good. I gotta look into these boards. I might get one of these for myself. Full size PCI Express. Really nice. It's a really nice board. It's the first time I see this one. That's why I'm so surprised that it has all those connectors, but no signs of melting or any damage to anything. So the majority of cups are solid state cups, so even if they get overheated, it's not a big deal. The majority of them on the back side, so no electrolyte. So this should be fine. Alrighty, so that was the free repair for Brian. Now we just need to get the return address, and the board is ready to be tested. Hopefully it works. If not, well, you can go ahead and send it again. I still have the second socket that you sent me. So feel free to send it again if there are any issues, especially since I melted a little bit of the socket while resoldering that cap. But I don't think that should impact anything. Alrighty, that's the AsRock Z790 PG ITX TB4 microboard and the socket replacement. Thank you guys very much for watching. I do appreciate you, and I shall see you in the next one.